Good afternoon. My name is Jack Hidary. Thank you, Brian. Thank you very much. We're going to hear from Brian in a second. And what I'm going to do for you today is reassemble this car motor with my mind. No, I'm not going to do it. We're going to get back to that in a second. I'm going to ask you two questions first. How many folks here, when they were in grade school, had a class like this? Wood shop, auto mechanics, things like that. Wood shop, auto mechanic. How many had that? Okay, very interesting. So we know that years and years ago, in those times, we had classes like that. And what happened recently? How many people here have grandchildren who have that kind of class? Grandchildren who have that kind of class. Children, one. So something has happened in the United States of America. We had something very special going on in this country, and we lost something. Now let me ask you a second question. There are 60+ million kids right now in grades K through 12. Grades K through 12, 60 million kids right now in school. Prediction from the audience. How many of those kids, say this year, in this grade right now, graduating from college right now, are graduating in science, tech, engineering, or math? Anything related to those fields. Any kind of science, any kind of technology, computers, engineering, math, anything like that. Out of 60 million total K through 12, now this grade, right now graduating in 2011, May of this year. Any guesses? 15%? 15%? 10%? Okay, it's getting more pessimistic, I guess, as we go on here. Great. Well, so hands-on science and tech. Let's talk about where we are today. 4 million kids were in 9th grade in 2001. 4 million kids of those 60 million I mentioned before were in 9th grade in this country in 2001. And here specifically, I'm talking about kids in public school. And what happens over time? This is something that we did with Raytheon. Raytheon and other partners analyzed what happens to kids over time. And we see a leaky pipe. In 2001, we had 4 million 9th graders, 2.79 high school grads, 1.8 get into college, 1.3 college ready, 277,000 majoring in STEM, science, tech, engineering, math, down to 166,000. So that's what's happening right now. That's what's happening right now. What happened back in 1957? What event triggered in this nation? Sputnik. And at that point in time, kids went in their backyards and they blew up rockets. Hopefully not themselves, but blew rockets into the sky. They were creative, doing all kinds of crazy things. You heard in the economics panel this morning, a number of the speakers speak about how we have technology, then we have to marry that to the unique American creativity, the enterprising nature of our young people. We need to marry that. Well, this is what's happening right now. These are the stark numbers that we're facing today. Let me put that in further perspective. China, producing 1 million STEM graduates this year, and increasing. Now again, it's not just about quantity. It's also about what they're capable of. How do you now look at a generation of students, of young people joining the workforce? How do we prepare them not just to know some facts and figures, not just to know some equations, not just to remember some facts about biology or the body, but to be creative, to be innovative, to create new companies, to create new technologies, new medical devices? That goes beyond even just the knowledge issue. How do you do that? Well, we knew how to do that once in this country. We knew how to do that. We knew that workshop and auto mechanics and things like that, these kinds of programs actually worked. They got the juices flowing, we gave a challenge to the kids, and they got going with it. And resulted in the biggest boon and biggest creation of wealth and innovation this country has ever seen. But now it's time to get back to that because we have lost our way there. We must come back to that. Hands-on and challenge-based. Let me define those two. So hands-on means not using textbooks as your primary mode of learning. It means getting your fingers dirty and wet. It means taking apart motors, putting back motors together. It means creating stuff. Challenge-based. Being hands-on alone is not enough. If you go into a laboratory today, a class laboratory, it's got beakers and Bunsen burners and nitrogen and hydrogen. Is that hands-on? Well, yeah, there's a hands-on aspect to it. But what are those kids doing? They're reading from a lab, call it procedure. They're reading a recipe. They're following a recipe. That's not challenge-based. Challenge-based is when you walk into a class and you offer a challenge to the kids. Kids, here's some Lego. Here's lots of Lego. You're in 4th grade, 5th grade, 6th grade. Challenge on the board. Build a robot that jumps across this stage. The teacher then pairs them up into groups of 3 or 4. They have to build their robots without instruction, without prior knowledge of how to do so. They will iterate. They will fail initially, and then they will succeed. We can bring in mentors from the outside, engineers from Boeing or Lockheed Martin, to mentor them as they're doing their thing. Iteration, failure, and then success. What is that called? That's called real life. That's called the kind of problem solving that we all each do every day. When we build businesses, when we solve tough problems in each of our careers and lives, it's called iteration. First failure, then success. That's how real life works, and that's what I believe we need to bring back into learning. And by the way, you might say, how will these kids do on standardized testing? It's great that they can put a motor back together, but how about the SATs? How about the Ohio State exam? Well, guess what? We have the data now. We have 5+ year longitudinal data that tells us that kids who are doing this kind of curriculum, who are doing this kind of approach, not only are creative, not only are excited, not only are staying in school, but they're doing better than their peers on standard, state, and federal exams. And why is that? Because they will learn that calculus equation. They will learn that piece of that fact that they need in the course of doing what they need to do. They will look it up on the internet. They will use a textbook as necessary, as a reference tool. And they will get that knowledge. So what do? We said, how do we scale this? We have this insight now. We have this data. What do we do with it? We went out to lots of corporate partners, HP, Intel, Business Roundtable. Some companies here might be part of the Business Roundtable, lots of folks represented in that. Other key partners were the National Science Teachers Association. We needed to engage with the teachers, work with them to re-engage the learning. American Chemical Society and 30 other professional societies of scientists, the physics, the physicists, and the chemists, and the biologists. We've got every kind of scientist in there. MacArthur Foundation, Bill and Melinda Gates Foundation. Went out to a lot of federal partners, NASA. There's more than 300,000 engineers in those symbols that I put up right there. 300,000 engineers that we, the taxpayers, pay for. We've engaged those as partners, bringing them out from NASA into the classroom, out from NIH into the classroom, out from NSF into the classroom, allowing them to interact directly, but not giving speeches. No speeches allowed. Only hands-on, challenge-based. And we built out a network called National Lab Network. What is this website? It is powered by an algorithm, a very powerful algorithm that's very much like Match.com or eHarmony. What does eHarmony do? eHarmony matches people based on characteristics. Well, this is not for dating, sorry. This is to match up K-12 teachers and classes with engineers, professionals, and others who want to volunteer, but don't know where and how. These are teachers who are out there saying, hey, I'd like to have a biologist come in from Pfizer, from Genentech, from Amgen. I'd like to have an engineer come in from Google, from HP. How do I do that? They make their request online. They put in the characteristics saying Fort Myers, grade, subject area. And sure enough, we have thousands of techie volunteers putting in their information, and the algorithm finds them. We launched this website in January of last year, January of 2010. This website is now used in more than 2,000 schools, and more than 500,000 kids have already done a program in the past 12 months based on this website. More than 500,000 kids. Thank you. Because, my friends, if we're going to do this at scale, it's wonderful to have a great after-school program, and I support tons of after-school programs that bring 1,000 kids or 5,000 kids, and that's great, and we should continue to do that. But both after school and during school, we have to start thinking about reaching 5 million, 10 million, 15 million. Our goal, as stated to our partners, is 7 million kids reached in the next 4 years. 7 million kids in the next 4 years. That will make it the largest education and learning program in the country. And we have to do that if we're going to change the numbers I showed you at the top of the slides. This is the website, nationallabnetwork.org. It's a nonprofit with all the partners I mentioned before. Teachers sign up, they post projects, they get matched, things happen. And now let me actually demonstrate something real to you. Right here in Fort Myers, we have a great school. It's a public school called Edison Collegiate High School. I believe the president of one of the Edison campuses here, Jeff Albritton. Is Jeff here? Was here? Here he is. Great. And this is a school. I want to welcome here 3 individuals. All right. Rebecca Hill, teacher, science teacher at Edison. Andrew Sun, student, 9th grade. And Brian Botts, principal of the school. Please welcome them. Rebecca, why don't you maybe give us a few moments before we put this together with our minds, a few moments on what your approach to learning and what your approach to science teaching is.
I approach science education very simply. It is challenge-based education. You can teach from a textbook all you want, and kids will become detached. They will become uninvolved and not interested. If you want to get a student involved in science, you have to challenge them. You have to ask them to stretch their minds and to problem solve. And so in my classroom, we simply approach it as we will give you all the tools and resources and support that you need. We will also allow you the time to explore a concept completely and come to your own conclusions.
Great.
I just wanted to briefly discuss with you a project that's going on in our classroom today, a challenge-based activity. Today is World Water Day in South Cape, Africa. South Africa, if you didn't know that, Cape Town, excuse me. Cape Town, South Africa. And the challenge in my classroom was to clean the water. And it was the Caloosahatchee River. And we gave the children very simple tools. We originally just gave them rocks. Stuff from Lowe's Garden Center, lava, sand, things that were very simple for them to manipulate. And what did they do? They failed fast, very quickly. They learned immediately how not to filter water. With the spirit of competition and challenge, they then learned from each other and became very good capitalists. They recruited their friends who could do it. They researched information, and they had another iteration of their design, and they implemented new things. They implemented soil. They implemented mechanical filters. And as you can see, this is one iteration with
so Rebecca, so explain to this is one of the filters that the kids built.
Yeah, that failed fast.
So it's made of multiple layers.
Yes. And
this one did not work.
No.
And one thing to note, by the way, that in most of this challenge-based stuff, you'll see this again and again. Are we using a lot of fancy materials? Are we using a $500,000 lab with beakers and Bunsen burners? No. We're using stuff from, household areas and things like that. Whoop. All right, excellent. This one is failing, definitely.
It's failing.
And then what did the kids do when they realized it failed? What did they then move to?
They then decided, well, how does it actually look in the environment? And if you were to look at a cross-section of an ecosystem, it would look a little more like this, a little more topographical.
It's almost like a rocket ship. These are different stages. These are 3 different stages that the kids put together on their own. Did you tell them how to do this?
Absolutely not.
Did you give them instructions exactly how to do this?
Absolutely not.
No, okay.
Yeah.
Andrew, do you want to explain maybe what this is and how you guys did it?
Really, we started, and she said, here you go. She gave us a little plastic cup, and we had a bag of rocks. And we got to work. We just put the rocks in and started doing things, and we tried to figure out what was going to work. And after we did this, and we filtered them many times, and we tested it, we realized, well, maybe this isn't going to work, and we tried it again. And each time, we kept taking a different look at it. And after we finally filtered this and we looked through it all and figured out how it worked, we were able to take that and connect that to our other core classes. In geography, we were able to take that and use hands-on learning to realize how people in other countries are cleaning water. In math, we were able to calculate river flows, the flow of the rate of the water. We were able to calculate the cost of this in other countries. In English, we were able to look at the culture that's also involved in this, where there's the culture and the poetry and all the writing. So it opens up a whole world, and it makes you want to get involved. Once you have one part of the project, you want to get it all done, and you want to get the whole picture.
So Andrew, when you were in 8th grade, you're in 9th grade now in this new kind of school, new kind of format, what kind of science did you have in 8th grade? What was your experience in science experiment labs?
In 8th grade, I went to a Lee County public school, and they are good schools, but lab day was take out this page in the workbook, rip it out on the little serrated edge, and go 1, 2, 3, 4, 5. Good job, you did your lab. Wait, we have one more post-lab question. There you go. Thank you. Enjoy your day.
Is this kid good or what? And so this is a fundamentally different approach. And you also had another hands-on activity where you had a challenge. And Brian, let me bring you in. Please welcome the principal of the school, Brian Botts.
Thank you, Jack.
Brian, do you want to explain what this challenge was?
Sure. As we finished the first semester of our year together, it was time to move from mechanics into chemistry. And so we needed a kind of a capstone project, something to really embody the spirit here. And so what we did was we just bought some small engines, and we set them up. We got the kids in groups. And then, without much direction, we just used technical terms like the black thing or the blue piece. And we just said to the kids, look, work with your group and get this piece off, and then kind of dissect it. Tell us what you think it does. See how it fits with the other things. What's going on here? And so we tried to help the kids understand what they were touching and seeing. And the real gem, the diamond in the rough, is this little part in the middle here. It's the timing gear from inside of a crankcase. And so for basically all 100 kids, 60 of which were young ladies, 40% of which were minority students, they were able to, with their own hands, rip this engine apart, identify that, take it out, put it back in. By the way, it was in time because when we put them back together, 8 out of the 9 ran, and then I fixed the last one. So we ended up with 9 rerunning engines that had been completely dismantled without one piece of technical knowledge from an adult to a kid. Every kid in the school took a test. They knew the names of the parts. They knew the functions. They knew the subsystems. They can troubleshoot an engine.
Great. And now you, Rebecca, and Brian, you now are bringing external adults into the classroom, working with them?
That's correct. As you might know, I'm not an engine expert. I am the science teacher, however, so I facilitate that experience. And in this case, we brought in gentlemen that were very versed in mechanics. Within the course of my careers class, I have environmental engineer that has come in and spoke. In the case of aquaculture, I have family friends who fish, and that's simply how it is. It is a valuable, I should say, invaluable resource to imagine being able to be paired up with that person in this, business today.
Great. Can we just have the slides back for 1 second? So in summary, and by the way, just to let you know, even when there's no person right there, we often can Skype in. This is a remote classroom that doesn't have some scientists nearby. We Skype in. And in summary, this is a revolution that is now underway. You see here evidence right now of how this really brings the creativity of kids out. Kids want to learn. They want to stay in school. It changes. And by the way, here's some great news. Not only in many of the schools that we work with are the grades up in science and math and tech, they're up in reading and writing as well. The kids are more engaged, they're more excited, they're working with their English teacher as well to also get involved. But this is critical right now. If we want to stay competitive, be innovative, it is absolutely critical now that we engage at scale these kinds of things that we had many years ago. Thank you very much for joining us. Thank you today.